Um, Thanks, everyone. So I'm happy to be presenting on behalf of my collaborators on our work on neural network verification. So at DeepMind, we're working towards building general purpose artificial intelligence that has very powerful capabilities. And the hope is that once you have very powerful AI, you can take any real-world task that you're interested in solving, encode it using the appropriate reward functions, loss functions, and give it the right kind of training data, and it should be able to solve all kinds of problems for you. And we've already achieved successes in diverse domains like analyzing retinal image scans, cooling data centers, and folding proteins. And even in the broader machine learning community, over the last 10 years or so, we've seen incredible performance on very complex image classification tasks like ImageNet. And so you might wonder, is this path going to continue, and are we kind of done, right? Unfortunately, along with the successes come some intriguing failures. And one of the common failure modes in image classification is this phenomenon of adversarial examples, where you can take a very powerful state-of-the-art classifier and add to it a very small amount of carefully chosen noise, and it starts to think that tabby cats look like guacamole suddenly, right? So the question is, where is the issue? And our thesis is that trying to define tasks for AI systems using just loss functions or training data is insufficient, and we need to go beyond this and think about formal specifications that we think our AI system should be consistent with, and essentially have ways to both train our AI systems to be consistent with these specifications, but also once they're trained, we want to verify that the trained models are indeed truly consistent with these specifications. So what are the specifications? So the one example that I already mentioned is this invariance to small perturbations, right? So if you take an image classifier and you corrupt its input with a small amount of noise, you want to make sure that the classifier still continues to produce the correct classification. But this is not the only example. Another example that we worked with in the past is if you're training a model of a dynamical system like a pendulum, and you know that the pendulum has a dissipative physical property, so it's going to lose energy over time, you want to ensure that your trained model is also consistent with this property of not gaining energy over time, right? Or if you're doing some kind of functional regression problem and you know that the functions you're interested in are monotonic, you can try to require that the functions learned by a neural network are also monotonic, right? And there's many more examples, and feel free to come and talk to me later if you're interested in other examples. So in today's talk, I'm going to focus on this problem of verifying robustness to small changes, but the techniques that we develop are actually more generally applicable to any input-output properties of neural networks, right? So we're going to be focusing on classifiers which have a layer architecture that interleaves convolutional or fully connected layers with a nonlinear layer composed of ReLU activations. And we're going to denote the input to the neural network as xn. So it takes an image of a 9 and correctly classifies it as a 9, right? But guided by our specification, we're interested in trying to ensure that the output label remains a 9 for all images of the form 9 plus a small amount of noise, where the noise is bounded in some norm by some parameter epsilon that we think should control imperceptible changes to the input. So if we look at trying to put this as a formal specification, we're going to look at the neural network and the intermediate activations in the network. And essentially, our specification is the difference between the logic corresponding to some incorrect label of the neural network and the logic corresponding to the correct label. And as you can see, this is typically a linear function of the penultimate activations, because usually at the end of the neural network, you just have a linear layer mapping the penultimate activations to the final logits. And so essentially, you just have a linear function of the penultimate activations. And we're going to require that the specification should be bounded above by 0 for all inputs within the epsilon ball, which means that the true label will always score higher than any of the incorrect labels for all perturbations of the input within this epsilon ball. Okay. So if you think about solving this or trying to ensure the specification, you can try to look for violations of the specification and you can solve an optimization problem that looks like this. So you want to maximize this specification, which is a linear function of your penultimate activations, subject to the constraints that your intermediate activations are consistent with the layers of the neural network, right? So the activations at layer k plus 1 come from applying a ReLU to an affine transformation of the activations at the previous layer, where the affine transformation can come from either a convolutional or a fully connected layer. And then if I go all the way back to the input, then I want to ensure that the input is within this epsilon ball of the nominal input that I started with. Okay. So, so the question is, yeah, suppose I could solve this optimization problem and I prove that the optimal value is smaller than 0, then essentially I'm done. But this is often a quite challenging task. So we can try to get some intuition for how you might go about verifying the specification by looking at the geometry of this problem. So you start with some set of perturbations of the input. And in this case, if we choose the L infinity norm to control the size of the perturbations, then you're going to get a box-like set. And then we're going to look at how this set propagates as we apply the various transformations at each layer of the neural network. And you can imagine that it starts out looking simple because you just apply some affine transformation, but then as you go down the various layers, because you're composing several nonlinearities, you can end up with a set that has an arbitrarily complicated geometry, right? And our task is to ensure that this set does not cross the specification boundary. In this picture it does, so we want to detect whether it crosses it, and if it doesn't cross it, we want to get a proof that it doesn't cross, right? So if we could compute this final set efficiently, then we will essentially be done. But that's a very challenging problem because it involves evaluating the neural network at every possible input within this set. And because of the high dimensional nature of the input space, this would quickly become intractable. Okay, so how much you go about solving this issue with the high dimensional space? One obvious idea is trying to sample the input space. So you could look at a bunch of samples and look at how those samples propagate through the neural network. If you do this, then you would estimate that this point here is the one that's closest to the specification, and it actually doesn't cross the specification boundary, which might lead you to incorrectly infer that the network was robust, although there was actually an adversarial example that does cross the boundary, right? So essentially, sampling can, especially in high-dimensional spaces, miss points that actually violate the specification. You can try to be a little bit more systematic about it, and this is the technique used in adversarial training, which is a very effective method for training robust networks, where you try to do local optimization starting at some guess for what the optimal adversarial example might be. And this is significantly more effective than sampling, but still in certain cases, because of the non-convex nature of these sets, you can end up finding these suboptimal adversarial examples which actually miss the specification violations, right? What a lot of researchers have done in the past few years is to study this problem using the framework of convex relaxations, where rather than trying to compute these sets exactly, you compute these bounding convex sets that outer approximate the sets that you're interested in. And if the bounding convex set does not cross the specification, and that you can answer using just solving a convex optimization problem, then you can conclude that your network was truly robust, right? Unfortunately, the problem here is that if these bounding sets are quite loose, then in many cases, even though the network was robust, you would not be able to conclude that based on this approach, right? So essentially, we are trying to ensure that these convex sets are as close to the true set as possible. And this is what we call the tightness of the relaxation. So essentially, in this case, if you have a set that's a very loose over approximation of the convex of the true set that you're interested in, then we call that a loose relaxation. And ideally, we want to go from loose relaxations towards tight relaxations that essentially compute a very tight bound on this non-convex set, ideally intersecting with it exactly at the point where you have the optimal adversarial example. Okay, so let's think about how people have constructed these relaxations in prior work. So the key ingredient is to look at the activation functions that appear, and the ReLU function is the one that's most often been studied, although you can extend this to other activation functions. So if you look at the ReLU function with input bounded between some number L and some number U, then essentially the graph of the ReLU function looks like this. It's going to be flat for the parts of the input that are smaller than 0, and then it's going to be equal to the input for the parts of the input that are larger than 0, right? And so this union of these two line segments is a non-convex set, and I want to compute some kind of convex set that bounds this. And so essentially, one idea that people have explored is to essentially bound it by drawing two line segments that are kind of parallel to each other that bound this union of line segments. And the advantage of this way of doing things is that you actually get a closed form solution for the resulting convex optimization problem, and this gives you a very fast and scalable verification method. You can try to refine the approximation a little bit by considering 3 linear constraints to bound the ReLU. And in this case, you get a more general convex optimization problem, typically a linear program. And so you have to solve a large convex optimization problem, which is slower, but it still kind of scales to rather large networks. Okay, so all of this sounds great, and you know, people have achieved a lot of success with this. But the main issue is that all these approaches relax each neuron independently. So they don't consider the correlations between the neurons in the network. So typically when neurons, the values of neurons move, they're going to move in highly correlated fashions because all of your transformations have a lot of structure to them, especially if you have convolutional layers and stuff. And so essentially these approaches tend to lead to quite weak relaxations. So there was a breakthrough at NeurIPS last year where the authors constructed what are called semi-definite programming relaxations, which look at the joint space of activations of multiple neurons. And by doing this, you can actually get significantly tighter bounds on this space of possible activations. So you can show empirically that these relaxations end up being tight, and the authors did so in the paper. But trying to solve semi-definite programs with off-the-shelf solvers is hopelessly intractable. And so we're interested in 2 questions. The first is, can we understand why these semi-definite programming relaxations are actually tight? And also, can we use this understanding to speed up solvers and scale these relaxations to much larger convolutional neural networks? Right? So these are the main contributions of our paper. So if we go back to the geometry of relaxations, the kinds of linear constraints that I was talking about typically lead to these convex relaxations that are defined by a set of linear constraints, so which, as we saw, are loose relaxations. In this semi-definite relaxations, you can think about it as propagating quadratic constraints, which are essentially ellipsoids in general orientation and position. And using the right kind of ellipsoid, essentially, you would hope that you can actually very accurately capture the geometry of the set you're interested in. So this gives you much tighter relaxations, but it's both computational, both in terms of computation and memory, it's much more expensive because you have order n square variables to optimize, where n is the size of the layers in your network. So essentially in our work, what we do is to try to find middle ground. So what we do is to restrict ourselves to axis-aligned ellipsoids. So we are going to fix the orientation of the ellipsoid to be aligned with the axes. And then in this way, we essentially get only order n variables to optimize. And you can take these axis-aligned ellipsoids and refine these by adding further linear constraints. Right. So the question is, when is this relaxation tight? So we're going to first analyze the original semi-definite programming relaxation that propagates the general ellipsoids. And we're going to use the following quantities in our analysis. So the first is, so I'm going to present the results just for a network with a single hidden layer. Right? You can extend it to multiple layers as well, but it's much easier to state the results for a single hidden layer. So we're going to look at the optimal adversarial example, the sensitivity of the linear specification at the optimal adversarial example, which is to say that if you compute the optimal adversarial example and you change it a little bit, how much is the objective of the specification going to change? We're going to look at the margin of linearity, which is essentially a measure of how far you have to move from the optimal adversarial example before you hit a nonlinearity of the ReLU function. right? Because the ReLU function only becomes nonlinear when you cross a 0. So if you look at the absolute value of wx plus b, essentially when the wx plus b becomes 0, that's where the ReLU will actually hit a nonlinearity. And so S star is kind of the margin of linearity. So it's basically saying how far you would move before you hit a nonlinearity of the ReLU function. And in this case, you can prove that if all the coefficients C are negative, then essentially this ends up being a convex optimization problem and you don't need any relaxation at all. So in some sense, this object max of C and 0 is the degree of non-convexity in this problem. So essentially for this semi-definite programming relaxation, you can prove that if this matrix that depends on these quantities is positive semi-definite, then essentially the relaxation is going to be tight. And you can interpret this as trying to say that the normalized sensitivity is larger than the ratio of the degree of non-convexity to the margin of linearity. So the only thing that changes when we go from this general semi-definite programming relaxations that consider this arbitrary ellipsoids to our relaxation is that we require that the same matrix is now diagonally dominant, so which is a kind of stricter condition than saying that it's positive semi-definite. So in some sense, like you can expect that our relaxation would also be tight in a large set of cases, except that we require slightly stricter conditions. And you can show that all of this analysis extends to much deeper networks, and essentially it just requires that the optimal adversarial example has some area around it where the network behaves in a linear fashion. And people have shown in recent works that like adversarial training techniques indeed actually create networks with this property. So if you do adversarial training, you end up with networks where you have this local linear behavior around the optimal adversarial example. So I'm going to quickly skip through some results. So we're going to compare to this standard semi-definite programming relaxations on small fully connected networks. And there we can see that our networks are able to achieve a tighter bound on the verified error rate very quickly, whereas the semi-definite programming relaxations take much longer. And we can also compare it on larger networks on CFAR, and there we see that if we consider various networks which have various trade-offs between robustness and verifiability, essentially the verified error rates from our relaxation are systematically better than previous methods, although we still have some to close the gap. And yeah, with that I'll close. Thank you.